time. Thank you for coming in. My name is Wilson Fandino. I'm one of the TA2s for this course. Just to tell you a little bit about myself. I'm a consultant anesthetist working here in London, and I have strong interest in clinical research, but especially in terms of the quantitative methods of clinical research. And I just volunteer myself to make like a tutorial in Stata, just to show you some tips and some important things that you should know when you are getting used to Stata. So I haven't delivered this presentation before, but so therefore I don't know how long it's going to take me, but I'm going to try to split my presentation in 3 parts. The first part is going to be like introductory part, hopefully no more than 5 minutes, and then we are going to talk about the descriptive statistics. We are going to talk about central tendency measurements. And then the last part of the presentation, if we've got some time, we are going to dedicate our time to look at the commands to compare means, which is the more basic, but I mean, we can always arrange a second meeting if we have no time to discuss this. I'm going to talk for about 30 minutes, and then we can have 3 minutes of break, and then we can continue. But I will try to make this as interactive as possible, okay? So to start with, I'm going to close this, and this is my Stata. So what is Stata? Stata is a statistical software package. Stata is short for statistical data, but this is not the only statistical software package available in the market. So you also have SPSS, and you might heard about the program R. And there's another program which is called Epidata, and then there's another one which is called Epinfo. All of these are very useful, obviously, statistical software packages. And the one we are working with is Stata, but as I say, it's not the only one. In my experience, I think South American countries, Central American, and in America, they tend to use Stata, but here in Europe, we tend to use more SPSS, and then the R is a program coming from New Zealand. SPSS came up in late 1960s. Stata came up in 1980s, and R is something more new. But Epidata and Epinfo is the official statistical software package for the CDC in Atlanta in the US, but this is more dedicated for purely epidemiology. And this is a Spanish one. Obviously, it comes in Spanish, but it's also useful for epidemiology as well. But in terms of statistics and clinical research, I would say these are the most important ones. SPSS, I would say, in my, and this is a personal opinion, it would be more intuitive than Stata. Stata is slightly more complicated because you have to understand the commands, and R, the one which is called R, is definitely more difficult to understand because you have to have a strong background in mathematics. I'm going to show you how to, I'm sure I showed you before, but I just like to show you how to import a file from Excel. So very quickly, I'm going to create some data here. For example, if you have this data, this is just a demonstration. I don't have any data set. but I just wanted to show you how to do this. You have, let's say, this very short data set, and then so you save this. I'm going to save this like, I don't know, office hour 7 of June, something like this. And then I'm going to save this, and then I'm going to go to my desktop. It should come up here, and then I'm going to copy this, and then you can go to Stata. And then you can simply say import Excel using your data. And then it's important to say first clear, because when you say first clear, for example, this variable is going to be called the group, and this variable is going to be, for example, mean blood pressure. So you import this data, and so Stata is going to understand that this is a number and this is a number, so it's going to create a conflict. So, so this is why you have to type first clear before, in order to tell Stata that don't disregard this first column or this first row in order to get the right data set. So first clear, and then you can see here in my data editor, it should come up your data. The other way to do this is a very easy one, which is just copy the data, and then if I go here, I'm going to clear this, and then I'm going to go to my editor, and then you can just paste your data, and you got your data there. Okay, great. So now I'm going to talk about this is a small package, small statistical package. That means that it only supports about 300 patients, no more than 300 subjects. And one of the advice, obviously I don't have any conflicts of interest at all, but one of the advice I could give to you is just acquire this small statistical package. You can purchase this for about, I don't know, it's like $120 American, and then you can have a lifetime license, and you can play with your data if you are interested in this in depth. Now I'm going to show you some useful commands, but this is very, very, very general ones. The one I wanted to show you is, for example, find it. But before this, I would like to tell you a couple of things. The first one, as you might already know, that Stata is very sensitive to the upper cases and lower cases. So that means that you type Anova in uppercase, Stata is not going to understand this is Anova, so you have to be really careful with the lower cases and the upper cases. The second tip I would like to show you is that Stata accepts the truncation of the or the abbreviation of the commands. For example, if you are going to summarize something, you don't really need to type summarize, so you just need to type sum, and that Stata is going to understand that this is summarize. Sum is for summarize, is not for summing. For example, if you are going to generate some data, generate. So you don't need to type the whole command, you just need to type gen, and that's it. So that's why sometimes it causes confusion, because no one understands what gen means, or no one understands what, for example, display So instead of display, we just use D, and Stata is going to understand that this is display. So this is very useful to know as well. And the other thing I wanted to show you, let me just create some data here. I believe I can run a t-test with this small data. So let's get a t-test. For example, variable 1 equal to variable 2. This is a pair. This is a pair t-test. T-test variable 1 estimates not found. Oh, sorry. This is why Stata is very sensitive to the spelling, obviously. So t-test. So you see here, for example, a t-test, and then you wanted to, for example, for your assignments or for your research project, you want to export this output. So you just need to copy this. I'm going to copy, and then you open a Word format, a Word file, and then you paste this. But then you can see that it's quite different, isn't it? The output looks completely different, and sometimes we don't really understand the output. So what I usually do is just change this to Courier. So Courier here, and then you change this to the size 9, then you're going to have exactly the same data. So I think it's a nice tip to, for example, for your presentations or for your research.
What an amazing tip, Wilson. I'm sorry for interrupting you, but what an amazing tip, because when I was a student, I got really freak, and sometimes I cut and paste the print screen, and then I was not able to highlight. And wow, thank you so much. So, could you repeat?
In that case, you just need to highlight whatever you want. I don't know, maybe you want to see this, or you want to say, look at this, or look at, I think it's very useful as well. Okay, so let's forget about this. So don't forget Courier size 9, and then you will have all the data presented in a right way in a Word format, okay? I don't need to save this, and I think that's it. Okay. Now I'm going to show you some useful commands. The one I wanted to show you first is the command find it. You probably have, well, maybe some of you are already used to Stata, but this is a useful command because it's actually the help from this data. And then you can type whatever you want to know. But for example, by the way, find it is the short for find it, but obviously Stata doesn't tolerate any spaces, so you just find it. So for example, I wanted to know something about the chi-square. Let's see. And then immediately it's going to come up some help from Stata. So you have some problems with the, I don't know, with whatever you want with the commands, or you're struggling with the commands. So this is the official help from Stata. So you can type on this and see what's going on with the function, understand more the system. I think this is useful as well. And it works for everything. I mean, you can learn more about, I don't know, for example, Anova. So let's find what Stata thinks about. So there's lots of information about Anova, and then you can search that. I think this is useful as well. In terms of the layout of the Stata, so as you can see here, I have the command here, but this is the outputs. You got the variables here, and then you got the Stata records the commands here. And then, for example, if I wanted to test again, I'm going to do a t-test. You don't really need to type the variable. You just go here and variable 1, this is going to appear here, and then you just need to type equal, and then go to variable 2, and then this is going to appear here automatically. So it actually prevents us to make some mistakes on the spelling of the variables. Obviously, this is quite easy to type var1 and variable 2, but imagine that you've got, I don't know, a data set of 600 patients with 20 variables. So you've got all the variables here, and then you don't need to type the variables. You just put it here, and then the variables are going to come up immediately there. Yeah. And the other thing, if you make a mistake, for example, here, and then you can retrieve the commands. For example, this one is going to appear here, or you want to repeat the command, or maybe you made a mistake, so you don't need to type again, because this is quite time consuming. So you just need to type here, and then this is going to come up immediately here. Okay. So you go to functions here, the data editor and the data browser. So the difference between the, by the way, you can type here, or you can just type here add for editor, and then you go for editor, or you can type here BR for browse, and then you go for the browse. So the difference between browse and edit is that in the browse mode, this is like a safety measure from Stata that you can't really modify. You can modify your data if you are in the browse, and then you can change to edit. So Stata usually asks you if you are short, you want to swap to edit. So I'll say yes, and then here you can actually modify your data. So you can create more variables, whatever you want. Some other comments that are useful, for example, let's say you want to drop a variable for whatever reason. So I'm going to go for the editor. And then, for example, let's say I don't need this variable anymore, the var2 anymore. So you just need to type here drop. This is the command for eliminating the variable. So drop the variable 2 and enter, and then you will see here that you actually eliminated the data. And when you finish with this, when you are going to close this, so you just need to clear this. Clear, you have to be careful with the clear command, because if you really type clear, Stata is going to understand that you don't need the data. So it's not going to ask you if you want to save the data. And then you lost the data actually. So you type clear, you are going to actually clear the data set. And you want to exit the program, just type exit. And as you can see, I don't have any access to the Stata anymore. So let's go for some other comments. I'm going to create some other comments here. Some other variables, sorry. Great. So
just one doubt. How we change the name of the variable?
This is my next.
Sorry.
This is my next comment. So obviously, it's very difficult to understand what the variable 1 means or what the variable 2 means. So actually, let me just change this to make more sense. Let me, for example, say that this is the group 1, this is the group 2. We got a data set of 10 patients. 5 patients are allocated to the group 1 and 5 patients to the group 2. Yeah, so so obviously it's very hard to remember, oh, which one is the group, the variable 1 or the variable 2. So you just need to rename. Rename is the command for Stata. So rename, and the syntax is rename all new. Yeah. So what is the old variable? So the old variable is variable 1, and then the name for my variable is going to be group, for example. And then I'm going to rename the variable 2, and I'm going to say, for example, I don't know. I don't know. I'm just making up something. Right ventricle thickness or something like that in millimeters. So as you can see here, data editor. So Stata has just changed the variable for you. So this data set makes more sense. So we already know that the group is the group, and the right ventricle thickness is this one. Okay. So what else? You can generate some more variables. As I said, there's a command which is called generate. You don't need to type this, just need to type generate. And for example, generate, for example, gender. Let's say gender equal to point, for example. And then Stata has just generated 10 data here, hopefully. And this, the point in Stata means that there is no data there, okay? So you can actually modify this with whatever the gender is. We usually codify the gender like 1 for male and 2 for female, for example, something like this. Yeah, and then you can generate new data as much as you can.
Wilson.
Yes.
Wilson, can you do operations?
This is my next. This is my next topic. Yeah. So
sorry.
The Stata can make some useful, or is actually is a calculator. So the way to do this is display. Display, okay? So as I say, you don't need to type display, you just need to type, for example, this or D or whatever. So display what? Display, for example, 4 plus 9, let's say. So 4 plus 9 equals 13, obviously. Display 89 minus 34. 89 minus 34 is 55. Say display 45 star. Star is the multiplication in Stata. For example, this one. So this is the 45 times 456 equals to 2,520. Display 67 over 76. This is a derivation there.
Actually, sorry,
yes.
I meant with the columns, like column variables in column B minus the variables in column 1 multiplied by 2 or something like that,
Yeah.
as we do in Excel.
Yes, exactly. Let's multiply this, for example, I don't know, maybe the square. Let's use the square to see. So generate RBT equal to, RBT square equal to RBT. Is squared actually, to see what is stated. So you understand this? I've just generated a new variable, which is going to be RVT squared. And that variable is going to be equal to RVT squared, actually. So let's see what Stata did. So this is my new variable, and then 45 by 45 is equal to 2025, and so on. Is that what you ask, Daniela?
Yes, but if I want to use two columns, like RVT squared minus RVT.
Yeah, you can do this. It's actually we use this in modeling as well. So let's see, for example, generate. I'm going to generate a variable which is called Daniela. And then this is going to be RVT squared. RVT squared minus 2. So I just generate a variable which is called Daniela. And this is going to be RVT squared minus 2. This is just an example, obviously, but you can do as many combinations or as many operations as you want. So you see that this generate command is very useful as well.
And if we want to do multiple operations, we use the brackets?
Yeah, you can use the brackets as well. Yes, you can use brackets. You will learn more about this during modeling regression because you have to transform the data. So this is actually very good comment.
Wilson.
For example, what else?
Wilson.
Yes.
One thing that I got some time to understand and reflect regarding organizing your data. For example, as you showed us, your data is organized group and the value. And we can organize group 1 and group 2 in 2 columns differently. But we can use these both kinds of organization to calculate the t-test, for example. But how we type is differently because you organize your data differently, right?
Yes.
So you can organize using this group 1, 2, or 1, 2, 1, 2, and you having 10 patients in each group, and yes. All the results in only one column, but the command in this case will not be as PPCR team teach us and you type in the beginning of this lecture. So for me, it was a huge step when I realized that. When I understood how I organize my data and how to, because if you want to run the t-test using the command that a PPCR team give us during assignments and so on, with this kind of organization, we'll have a wrong output because the variable 1 does not mean the values of the outcome, right?
Yes. This is an excellent question, Karla. And it's actually a little bit tricky for Stata to convert the data, unfortunately. Especially, obviously, you have 5 patients and 5 patients. This is so easy. But the problem is when you are dealing with 600 patients or 700 patients. And so what Karla was, sorry, before I forget, now that you mentioned organize, and before answering your question, Karla, I wanted to show you something as well. So you see, for example, the RVT here, and then sometimes you might be interested in organize this data in ascending order, for example. So you see the data here. I'm going to generate another command, for example, generate RVT organize, something like that. Equal to point. So you see here there's a new variable. And then I think it's renamed. Let's see. No, it's not record. Stata. Let's see if Stata can understand this. No. Anyway, what I wanted to show you is that you can organize the ascending data. For example, sort the variable is the syntaxis of the sort command. So you can sort, for example, sort the RVT, and then you can see here that the new variable is sorted in ascending order. If you wanted to organize your data in ascending order, I don't know, for example, to see what the median is, or if you are interested in sorting data. Anyway, so
I have a question, Wilson. When you did the sort, did it change the whole table or only this variable?
No, just the variable, just this variable, just the RVT.
No, but then you can mix your whole data, because if each line is a patient and you sort only the column, it
Yes.
will mix it up, right?
Oh, definitely, yes. Yes, I think, yes, because Stata is not going to understand that that this one is for the group one or this one was for, so you have to be careful with this as well.
Okay.
I guess, Wilson, that Stata understood, because in the, could you show again your data browser, data editor?
Yeah.
Because when we see, for example, 12, we have a schedule, the correct values. I guess in this case, Stata understood that we organize all the line, because the values are correct, I guess. Squared 12, squared 21.
Yeah, you're right.
Yeah. I guess Stata is understood now.
This is smarter than us. Yeah.
Yeah.
You can see that actually this is organized as well. Yeah, so it's in ascending order as well, and this is in ascending order. So yeah, it's definitely organized, and then obviously the group is not going to be organized because it depends on where the patient belongs to. But yeah, this is the proof that Stata organized all the rows, because it's all nice and organized now. Thank you for that.
But maybe this is because they were a formula from the original RVT, and maybe the group and the gender.
But they
doesn't follow.
They understood that they understood the gender and the group also, because it was organized 1 1 1 1 and 2 2 2 2 regarding groups. So I guess every variable was organized based on the ascending order of RVT.
Okay, thank you.
Right, so, but it wasn't your question, Karla. I just wanted to show you this, but I'm going to clear this. And I'm going to generate some more data here. Let's say this is the, okay, so let me think. Let me just think first. So let's imagine that you've got 10 pages again, and then you've got, I'm going to generate my data, and I'm going to explain to you what I mean by this. Sorry. Sorry, it's going to take me less than a minute, okay? Okay, so I've got a data set here. I'm going to close this. And then I'm going to say rename variable 1 equal to patient, for example. Yes, sorry, data. And then rename variable 2, let's say this is a basal score, or maybe before any intervention, and then this is going to be rename bar3 after, and then rename bar4, for example, 48 hours, something like this. I don't think it's going to tolerate this, so maybe 2 days. Yes, so you can see here my data. And so what I've just done here is that we got 10 patients, and we are going to measure on the same patient before an intervention, and then on the same patient I'm going to measure after the intervention, and then on the same patient I'm going to measure at 48 hours. And this is what the data looks like. And can anyone tell me which test can you use if we are talking about normality and homozygosity? So this is a repeat measures Anova, right?
Yeah, but first it's important what if you want to evaluate only 24 hours after, or if you want to evaluate the, as you said, the repeated measurements. Because sometimes in your data you have this information, but your primary outcome was only the difference. So it's important. I don't know if students agree with me, please. It's not my classroom, but I'm take advantage from this meeting. But we should be really sure that before thinking about what's our primary outcome, what we want to evaluate, because it's really common when we have a big data set with a lot of information, and we should be aware what kind of information we want to evaluate.
Yeah, you're right, Karla. So I'm going to back again to my original variables. Okay, so now you understand what kind of I'm trying to do. And then, so as I say, it's a little bit complicated because you have to, I mean, the equation from Karla is how to convert this. This is called a wide format, and we have to convert this to a long format, right?
Wilson, can I try to answer?
Yes.
It looks like you have one, you have one independent variable.
Actually,
one group.
Yes, one group, which is the dependent variable.
Oh, dependent. Okay, so you have one group, and you have three measures, three time measures along the timeline.
So you can really say groups because this is the measure 1, measure 2, and measure 3 for the
No,
same.
measures, not
Yeah.
group. You have three measures. You have three values along a timeline.
Yeah.
Right. So would I choose the paired t-test?
No, you can do a pair t-test because you've got three variables here. So this is a good question as well, because if you had only this one and this one, this is a pair t-test. Only this one and this one, right?
Okay.
Provided that this is coming from the same patient, the typical example is before and after, before, after, before, after. So I created three variables to show you how the repeat measures ANOVA looks like. Does it make sense?
Yes. Yeah, I need help at this point. Anyone can jump in.
Yeah, I think Shubha, I have comment. This is the three measurement for one independent sample.
Yes.
So this will be one-way ANOVA because one sample.
This is a good question, Amani, as well, but this is not possible to do ANOVA. It needs to be a repeat measures ANOVA because you are measuring the same subjects. Okay. If these variables are completely independent, are coming from different groups, for example, for group 1, this is for group 2, and this is for group 3, this is an ANOVA. Yeah. But, because of the fact that this value, and this value come from the same patient, so this is a repeat measures ANOVA. I mean, you can't really do a simple ANOVA, and the repeat measures ANOVA is a little tricky in Stata, to be honest with you. It's not straightforward.
So this type of ANOVA, we call it repeated ANOVA. Yeah, like what is the difference? So what is the difference from repeated ANOVA and three-way ANOVA? Like, because we are doing three measurements. So three-way, it's different, that three independent sample. I mean,
so
it's not measurement.
This value comes from a different patient and different group. This value comes from a different group, and this value comes from a different group. But in this case, I'm going to illustrate you that the patient measure on the same patient. We measure before, we measure after the intervention, and we measure sometimes within 48 hours after the intervention. Now I'm going to try to do this. I'm not sure if it's going to.
Unlimited service costs and free repairs on covered parts.
But
Wilson,
yes.
Udo asked about it. I guess some.
Karla.
Sorry,
I think there is some noise in the background.
Yeah, I moved. I unmoved. Move the microphone. Regarding your question, Udo, I guess what Wilson is explaining us, because we have only 10 patients doing exactly the same approach, and we have 3 different measurements in one patient. It's not not one group, but in each patient. Yes, when we have more than two measurements in the same patients, we can't use the paired test, so we should use the repeated measurement ANOVA. It's, as Wilson said, it's not easy to organize and run this. It's not easy to run this test in Stata, because it's not, when we organize the data as Wilson said, as Wilson did, it's the rationale make us to plan in this way: one patient before, after, and 48 hours after. But to Stata understand our data, Wilson for sure will show us how we need to organize, reorganize.
Yes. So in order to answer your question and make some progress with the meeting, Karla, so the answer for your question is this one. You have to understand that the format I just showed you is called, for this data, is called wide format, and you just need to convert your format to the long format in order to run repeat measures ANOVA, right? So,
Wilson, from wide format to long format.
Sorry, did I say the other way around? Sorry.
No, I just needed to make sure I understood.
Yes, from the wide format to the long format. So you saw the format. Did you see the format before that? It looked like a wide format, yeah? So the comment is reshape. Reshape what? Reshape from the wide to the long, and then where are you going to reshape? I'm going to reshape the variable here, and then I'm going to indicate to Anova that E is my patient because I decide to give this this name for my variable for my patient. Yeah, so hopefully you can remember the data set what it looked like before, and then J for VA, which means that is going to generate 3 variables for the same patient. I know I mean, for me, it took me a while to understand this. This is not straightforward in Stata, but this is the way to do this. And then I'm going to go to the editor, and then you can see the difference. And you see that the difference between the wide format and the long format. So what the Stata did to me was, for the first patient, there were 3 measurements. So this is organized differently. So now I've got 3 measurements for 1 patient. For the second patient, I've got 3 measurements, and so on until my patient 10. You see that? And then this is the mean of whatever you are measuring. But I just wanted to show you what the syntax is for this data, which is not intuitive, is not straightforward to understand, but this is what we had to do if we are dealing with a wide format. That this is the same problem with the pair, with the t-test, because when you are, I'm going to, for example, I can do. So you understand this, yeah? Can I clear this? Anyway, it's recorded, so you can.
Yeah, I guess it's not easy to, but we understood what you want to explain us.
Yeah, we can move on. Yes.
I mean, it took me a while to understand the way that does this, but this is the way. As I say, this is not straightforward. This is not intuitive, but this is the way we had to do it, right? Right. So and I was saying that the same problem happens with the t-test, because whenever you have a t-test, let's say again, I don't want to spend a lot of time on this because I have to move on, but what happened here? Again, 5 patients.
Wilson,
Yes.
just a quick question. If you have a missing value in one of your measurements, what happens? If not all patients have 3 measurements.
So Stata is not going to accept your data. So you have to either, for example, you will see later on how to deal with the missing data. So you have to come up with the solution. I mean, it's not possible to miss the data there. You have to deal with missing data, and for example, I'm sure you remember the mean imputation and the last observation carry forward.
No, yes. So Stata will not do the calculations unless all the.
Yes.
Okay, thank you.
Yeah. So this is a t-test. Let me just think about this. What am I doing here? Right, sorry for the wait. So again, I've got two groups. You are comparing a continuous variable, and the group 1, you can see there are 10 patients here, and then there are 10 patients in the group 2. So this is not the right way to do a t-test, but it's still Stata can understand this. If you, because this is what Stata understand by the wide format, yeah. Whenever you come across with this data, group 1, group 2, and then the mean or whatever the continuous variable is here, so you have to run this syntaxes. So t-test group 1 equal to group 2. When you type this, Stata is going to understand, and this is really important, and your t-test is pair, okay? So if you wanted to run an unpaired test, you have to specify to Stata t-test group 1 equal to group 2, and the comma is very important, and unpaired. And as you can see here, so this is an unpaired. And actually, you can see that the p-value is quite different from here, and then the t-value here that I explained to you the other day is different from here and from here. Yeah, so this is important to understand that if you don't specify to Stata that your data are unpaired, by unpaired, by the way, I mean that sorry. By unpaired, I mean that there are 2 groups, and I'm not talking about this before and this after the first patient, before and after the first patient. If this is the case before and after, so this is a pair test, So as you can see, the output is very similar, but the values are different. So you have to be really careful with this. Okay. So the other, I'm going to clear this again. And then the other way to present this data is just this one. So you got a group here, and then you got a second group here, and then you got your continuous variable, whatever the variable is. So whenever you come across with this, so this is exactly the same context, the same concept. You got two groups here again. The first group, you got 10 patients, and the second group, you got 10 patients again, and this is the mean. And you just need to compare the mean of this. Your null hypothesis is going to be whether or not this mean is significantly different from this mean, okay? So as you see, the layout is completely different because this is a long format. This is not a wide format. I'm going to rename this very quickly. So rename variable 1 group and rename variable 2 RBT, for example, yeah. So so the syntaxes for the t-test in this case is different because it's going to be t-test dependent variable, comma, by independent variable. And then, sorry, by this, it needs to be in parentheses, in depth, like this. This is the standard syntaxes for the t-test, for the Stata, for a long format. So the dependent variable, what is the dependent variable here? It's going to be RBT, so RBT is here. And the independent variable is going to be my group. So group here. And then you can see here what I wanted to show you actually. So this is a t-test with equal variances. You can see here, I explained to you the other day that this is the t-value. So 0.9716, it should look exactly the same one as in the other format. I mean, I can demonstrate to you this because I changed the data, but it should come out exactly the same t-test. So so my point is that you can use this one, or you can use this one, but you can use those indifferently. It depends on the distribution of your data. And when I say distribution, I mean whether or not the data set is long or a wide format. I hope that
this Wilson, is the unpaired test, right?
This is the unpaired t-test.
Unpaired test.
And the only way to do the paired t-test is this one.
Okay. Okay.
This is the only way. Actually,
so if we have this long format, we should transform in the wide format to run the paired test, right?
No. In this case, you wanted to do a paired t-test. Stata can do that for you. So in the I'm still in the long format. You see, this is the long format. So you just need to change this t-test RBT. The other thing I didn't mention to you is that the dependent variable is always first. Dependent variable is always first. There might be some exceptions to the rule, but for most of the tests in Stata, always the dependent variable is going to come first. And it applies to Anova, it applies to t-test, it applies to Wilcoxon, to many tests, to many tests, okay? So t-test, dependent variable, equal, group. estimate not found.
I guess t-test, Euro test.
Thank you, Karla. Yes. So this is the parity test, and this is the unparity test for the same data and for a long formats. Okay, so as you can see, actually, can you tell me why this is so significant? Because the P is very significant. Why is significant? Because Stata understood that this is pair. This is the first patient, and this is pair, and this is before, and this is after, and this is before, and this is after. And obviously, 1 is very different from 32, and 2 is very different from 56, and 2 is very different to 45. So that's why standard misunderstood the command, because this is not a. So you see how interesting is this, because you are meant to do a pair test, and you come up with this with the wrong command, so you can actually report your results as very, very significant when they were not. You can see the big mistake.
Yeah, exactly this, Wilson. Exactly this what I mean when
Yes.
this situation, because it happens with me, and I saw, wow, this is significant, and so on.
Very significant.
But that's why I really believe when you understand your data and how you organize it, it must be the beginning, because sometimes just copying the command of the assignment, you will be able to answer the question. But if you can't understand, you probably make some big mistakes when evaluating your data or evaluating another or a different kind of data set.
Yeah, Wilson, I know this is going to be, maybe we can talk about it after your presentation. Let me bring it up then.
Okay. So I think I'm done with this section. I don't know if you want to have a breakout for about 2 minutes or 3 minutes, and we come back in 3 minutes.
Okay.
Sure.
Karla, thank you for your the two things that you posted in Gmail. Thank you.
You're welcome. You're welcome.
Yeah, that's very helpful. What I was going to ask Wilson is if he could give us some very simple tables to practice on, just one example for each type of test, like one for unpaired, one for paired, one for one-way ANOVA, one for linear regression, just one small project with just tables, you know. And I think if I get that, and I can just practice on my own with just those things, I think it'll turn a big corner for me.
Yes, so I guess Wilson can give us great tips, and Stata has some data sets to practice. If I can remember and try to search, I may help you, but maybe Wilson knows some names. STAs in general will have workshops and training about this on the 5-day immersion course, and last year we had. I can search in my notes to help you and suggest to you a data set, but Wilson maybe knows already.
Yeah, Wilson, I was just asking.
Yes, I heard your question,
yeah.
Shoba. I've got a table for you.
Yeah, just one like, you know, just 5 digits, you know, 5.
I don't have
in a data set. Yeah,
I will show you because I think it's very important to understand like a map what we are talking about.
Yeah, I know it's so much extra work for you, and
no,
I don't know how to compensate for your time, but
just remind me of towards the end of the meeting, and I can talk to you for about 5 minutes about this.
Okay, if I can get one example, a simple example for each, it'll turn a big corner for me.
Yes, we can come up with examples together, but
okay.
The important thing is that you understand the concepts.
Yes, yeah.
I think this slide I've got is very useful for you to understand.
Yeah, no, so far it's been good, but it's a lot.
It's a lot. It's a lot. I mean, it's I can't really talk about this in 10 minutes.
Yeah, I know, and I think you have simplified it as much as you can, you know.
I'm trying to, yes. So something that I forgot to tell you, and I believe is important as well. Let me just, am I sharing? Yes. Am I sharing my screen?
Yes, you are.
Yes, yes.
Right, so I still got my data here, and then I'm going to do the same test here. Yeah. Okay. So I've got a question for you. Do you think you could use Anova for this example? I mean, I'm just trying to compare two groups. One group with 10 patients and another group with 10 patients. So, and you've got the right ventricle thickness. This is something that I just made up. So my question for you is, do you think you can run an Anova for this? And I would like to see the chat to see for example, yes, not, or I don't know.
I'm sorry, I was muted. I think we have to look at the Stata table again.
Yes, sure. So again, my question for you is whether or not you can use an Anova for this. Can you use Anova? So just reply in the chat, yes, not, or I don't know.
Oh, okay.
So Sophia say yes.
But you said it was, for example, if group 1 has, for example, 10 subjects, group 2 has 10 subjects, and also to compare with RVT.
Yes, exactly the same data set. I'm just trying to compare 2 means instead of 3, only 2 means. So my question for you is whether or not you can run an Anova for this, because Anova is supposed to be used for 3 samples, isn't it?
Yes.
So then Daniela say that she believes that we can. Gisela said not. Showa said, I suppose yes. Sophia said yes. Gisela agrees with Daniela. Anyway, so I'm going to show you here. So what I just did here, this is my t-test. This is the standard one, yeah? And you can see here the p-value is 0.9716. Can you see this? And then can you see and then I run the Anova for the same data, for my same data. So by the way, the p-value you should look at is on the p-value of your model. So you can see here that should be exactly the same, yeah? 0.9716, 0.9716. So Anova is demonstrating you that Stata is demonstrating you that Anova can actually be used for 2 groups as well. I mean, we don't really use this for 2 groups, but we use Anova for 3 groups, but technically it should be exactly the same output, yeah? So the 2 sample t-tests with equal variance for Ampere 1 is 0.9716, and the p-value for the Anova one is 0.9716, okay?
So on one of your earlier commands, it showed the paired and the unpaired on one screen. And this screen is showing the...
this is Ampere and this is Ampere. And these are 2 different ways to do exactly the same thing.
But in the other screen, it didn't show the Anova. So how did you pull this one out?
Oh, okay, sorry. It's exactly the same, Showa. So it's Anova, dependent variable, independent variable. That's it. You remember when I said the dependent variable is going to be always first, and this is always the rule. As I say, there might be some exceptions for the rule, but this is always like this: dependent, independent, linear regression, dependent, independent. Even for non-parametric tests, okay? So what is the dependent variable, Shoba?
I'm sorry, why is it dependent?
Which one of these variables is the dependent one and which one is the independent one?
The group is the independent.
Yes, so let's
put
the independent here, so group. And therefore, the dependent one is RBT, right? So this is the syntaxis for the Anova command, as you can see here. Yeah, Anova, dependent, independent, and you can see here the p-value. maybe next week or in a couple of weeks' time, you will have some time to discuss the ANOVA and the comparison between two or more groups. Okay. So
Gisela asked on the chat, and not asked but stated, and I understand her, that she believes that ANOVA it's only for 3 or more than 2 groups.
Yes, so ANOVA,
it's you're not wrong, but it's important to realize that t-tests are not able to evaluate 3 groups. ANOVA has this characteristic. ANOVA allows us during the process, all the calculation, to evaluate more than 2 groups. But it not means that ANOVA is not able to evaluate. It's just because in general, no, it's not necessary to use ANOVA for 2 groups, right, Wilson? But on the other hand, we can evaluate 3 groups using ANOVA.
Right. So the reason I'm showing you this is because actually ANOVA can help us with something that the t-test doesn't have. So you remember, or I don't know, I'm not sure if you have already discussed this, but in order to run a parametric test, you have to have some conditions. And the first condition is the normality of the data. The second condition is the homoscedasticity of the data, which is the homogeneity of the variances. The third one is that the data are independent, which means that the data are not paired, in which case, if the data are paired, so you have to use the pair test. And the fourth one is that data come from a random sample. Is that clear for you? Have you already discussed this in the course?
Yes, that is clear for me.
Yes.
That
okay.
to use ANOVA to use a pair t-test or parametric test, it's necessary to meet some assumptions.
Yes. Now I'm going to ask, for example, if I ask Daniela, how did you test the homogeneity of variances in a t-test? How did you realize, well, there is homogeneity of variances in my sample, so I'm allowed to use the t-test?
There is a test, Bartlett Test, right? I don't know if this is the name.
Well done, Daniela. This is the one I'm going to talk about, okay? So the problem with the t-test, and I'm going to run again my t-test, is here and here. I'm going to run I'm not going to run the ANOVA yet. But the problem with this is that the 2 sample t-test assumes that there are equal variances. Have you realized of this? 2 sample t-tests with equal variances. So who says data that it has equal variances? We have to check before if our data, if this RBT has got equal variances, which is called in statistics homoscedasticity.
Wilson, is that an assumption?
This is an assumption before running the test. So you have to, this is something that we usually overlook on the assumptions, and we just go straight to the t-test. But as you can see here, the t-test is, Stata is assuming that, that the RBT has got equal variances. But we haven't tested the equality of variances. We should have tested before. So as Daniela said, one of the tests, this is not the only one, there's another one which is called Levin Test. you can use the Bartlett Test or the Levin Test. I'm going to talk about the Levin Test later on, but I just wanted to say that you have to test the equality of variance. And one of the ways to do this, I'm going to run again my Anova, which is this one. So Anova doesn't tell me either what is the equality of variance. Did you know how to use this? So there's another way to run Anova, which is called one way. Okay, one way is the name of the commands, and then you just need to run one way, and again dependent variable and independent variable. Okay. So what you can see here is exactly the same output, 0.9716, 0.9716, 0.9716 for the t-test. It should be exactly the same because we are dealing with the same data. But can you see this?
Yes.
So when you are running a t-test, is useful, and this is the answer for Gisela's question and Karla's question, is useful to run an Anova in order to test the equality of variance. And then the Bartlett test is testing the variances. And then can you tell me, is it significant or is not significant? So the p-value is 0.0984. This is the number you should look at.
Not significant, right?
Not significant. Yeah.
It's not significant. So what is your conclusion? So is your data having equality of variances, or it doesn't have any equality of variances?
Oh, wow. That was amazing, Wilson. There was too much chance over here. Too much chance of error, too much chance of difference in variance, too much chance of whatever, bad things.
So so whenever
we are testing that the null hypothesis is that there is no difference, and we couldn't prove it otherwise. So there is no difference. So they have equal variances, right?
So whenever you interpret a test, always you should wonder yourself, what is the null hypothesis, as Daniela said. So so for normality and for homoscedasticity, for homogeneity of variances, the null hypothesis departs from normality and from homoscedasticity. So that means that if the null hypothesis is that there is homoscedasticity for equality of variances. And the null hypothesis, on the other hand, is that there is normality of the data, okay? So if the data is, if the p-value is more than 0.05, I'm going more than 0.05, I'm going to reject my null hypothesis of homoscedasticity. And I'm going to say, this is going to be not, this is going to be, it hasn't got equality of variances. Does it make sense? I mean, the null hypothesis is equality of variances. And the null hypothesis for normality is that there is normality, actually. If the data, if it's more than 0.05, if it's more than 0.05, so that means that your data is normal. And if it's more than 0.05, that means in this case that your data is homoscedasticity. I don't know if I did the other way around.
I guess it's so clear, Wilson, because when we understand the null hypothesis, as you explained us, when we know the null hypothesis that have equal variance and that we have normality.
Yes.
And if we can't reject it, so
yes.
we accept it.
Yes, exactly. So I'm sure you will understand this by my example. I'm going to clear my data. Can I clear this data? Is it clear for everyone?
Yes.
Yeah.
Yes. Let's go for another example. So I've got a data here which makes no sense, but I just wanted to show you something. So there is a command in Stata which is histogram, and actually you can. It's very useful to see whether or not your data is normally distributed and or is not normally distributed. So obviously there are some other ways. I'm going to talk about all the ways to prove normality and homogeneity, but I think it's very useful to start with a visual graphic to see what our data looks like, okay? So again, you don't need to type histogram, you just need to type hist, and Anova is going to understand that. So I'm going to make my histogram for my data. And I'm going to draw normality curve. And then I'm going to say this to Stata to see what it looks like. So I just wanted to ask you, do you think this is normal distribution or is not normal distribution?
Normal.
It's normal.
Is it
what is JISC?
Great. So so this is a normal distribution, but the first thing I need to say is that in clinical research, you won't come across with this data, unfortunately. I mean, this is something that I just made up, but you won't see this in clinical practice because this is a perfectly distributed data. So my first point is that you will never ever see this in clinical research. So that means that your data might resemble the shape of a bell, but it's not going to be like this never ever, because this is your data is supposed to be random. It's supposed to come from a random population, and I just made up this on purpose to create my normal distribution. So so this is why you will be surprised how many times you see the data and you don't really believe, oh, this is not really normal, but you run the test, you're going to realize this is normal, okay? So now I'm going to show you for this data, let me just remember. Yeah, so there are at least three or four ways to test normality in clinical research. I'm going to show you the first one is Shapiro-Wilk. Sorry about the names, but this is what the name is for the normality of the data, the test for testing normality. Shapiro-Wilk, and this is, I mean, it was first described like in 1969, and then something like 3 years after that, Shapiro developed the same data with Dr. Francia, which is a simplified version of the Shapiro-Wilk. And this is actually called the Shapiro-Francia test. And the other test I wanted to talk to you is the Kolmogorov-Smirnov. Yeah, and there's another test which is called quickness and kurtosis. Quickness and kurtosis test. I will show you these commands to how to run a Shapiro-Wilk, how to run a Shapiro-Francia, how to run a Kolmogorov-Smirnov or quickness and kurtosis. Now, before this, did you actually understand what quickness is and what kurtosis is?
I understood skewness. I need more clarification on kurtosis.
Right. Okay, so let me then go to this. So basically, the quickness is the measure of symmetry of the curve, and the kurtosis is the measure of the outliers of your data set. I'm going to show you, for example, let's go for this. New slide. So this is a normal distribution. This is a skew data, and this is another skew data. Should look like this. So you understand the difference is the skewness is the measure of the symmetry of the curve, okay? So this is completely symmetrical, this is skewed, and this is skewed as well.
Which one is left and which is right? Skewedness.
I can't remember really. That's a good question. I think the left side of the tail is the left side skewed, and the right side is the right side skewed. But honestly, I'm talking by heart. I can't remember which one is one. And the kurtosis, I did say that is a measure of the outliers. So so let's compare this. This is a normal distribution. So both curves are symmetrical. They've got good skewness. They are symmetrical, well, roughly symmetrical. This is symmetrical, and this is symmetrical, and this is the mean. And the median is going to be probably at the same point, and the mean here is going to be equal to the median as well, okay? So because this data has got more outliers here and more outliers here than this one, so this has better kurtosis than this one, okay? And I would like to see my data like this. I wouldn't like to see too many outliers because my data is going to be like this, and then I'm going to have problems with testing normality of the data. And this is why you have to test, and there is a way to test the kurtosis and the skewness. Okay? Everyone understood this?
Perfect, Wilson. Thank you.
I'm going to discard this. So back to my test. I know in the course, many people know the Shapiro-Wilk test and the Kolmogorov-Smirnov. A few people know about the Shapiro-Francia, and some people might know about this test, that there is a test for this. The first thing I would like to say about this is that the Kolmogorov-Smirnov is not straightforward in its data, and number one. And number two, and most importantly, the Kolmogorov-Smirnov was not designed to test any normality at all. So the Kolmogorov-Smirnov test was designed to test goodness of fit, which is another topic you will see when modeling, when trying to do modeling for regression. So you will see this concept, the goodness of fit. The goodness of fit. So the Kolmogorov-Smirnov was originally described for goodness of fit, and someone at some point said this: we are going to use Kolmogorov-Smirnov for normality. So I have to tell you that the Kolmogorov-Smirnov number one is very difficult to test in Stata. You have to download special software that you don't have in your Stata, in your basic Stata. And number two, and most importantly, Kolmogorov-Smirnov hasn't got any power, has got very low power to test normality. So I'm going to forget this. And then I'm going to tell you, before we move to the Shapiro-Wilk and Shapiro-Francia, I'm going to test the squigneous and the kurtosis, okay? So it's actually quite easy. Squigneous, kurtosis test and variable. So you see squigneous, kurtosis test for normality, and you can see the p-value for squigneous and the p-value for kurtosis. So you see my data. My data is perfectly symmetric. So this is why it's 1 here. The one here is perfectly symmetric. Yeah. As I say, you won't see this in clinical research. And then the kurtosis is acceptable because again, he's not looking like this. The curve is not flat. So it's actually a very good one. And the probability is going to be 0.64. Okay, so 0.64 is more than 0.05. It helps me to remind me of that for normality of data, this is, I mean, there's no doubt that this is normal. I mean, no one is going to say that this is not normal. And however, the test is not significant. So whenever the test is not significant, that means that the data is actually normal. Okay, and this is the same context for the homoscedasticity. So the fact that you don't have any significant p-value is actually good because that means that your data are normal.
Wilson, I found on the internet graphic that explains Sobha question. Maybe I'll try to share just to, yes. As I think it's easier when we are you seeing?
Yes.
Yes.
Yes, yes, Karla, thank you.
That's the right skewed and left skewed. So I guess Wilson I already answered, but just to confirm that left skewed, the tail is, the long tail goes to the left, and the right skewed, the long tail goes to the right.
Thank you.
You're welcome.
Mm-hmm. Thank you, Karla. All right, so I mean, it's really important to understand this because I mean, it causes a lot of confusion when you test the normality and homoscedasticity. So so my the message to take home is that whenever you see the p-value is not significant, is actually good for normality and for homoscedasticity, and that means that you can actually use your data for parametric tests. So this is the first one I wanted to show you. And the second one was Shapiro-Wilk. So Shapiro-Wilk is just S-Wilk, and then the variable. So do you think the Shapiro-Wilk is going to be more than 0.05 or less than 0.05?
More.
0.98. Yes, because it's perfectly distributed. Yeah. And then the other one I wanted to show you is the Shapiro-Francia. And again, is actually, I mean, all of them are telling me that my data is very well distributed, and as you can see, there's no doubt that my data is very well distributed, that there is a normal distribution here. Okay, and this is the way we test the normality. Is it clear for everyone?
Yes, thank you.
So regarding the homoscedasticity, there are two tests. The first one, we talk about this, which is the Bartlett Test. And then the other one is going to be the Levin Test. Levin Test. Before I forget, I want to tell you something about the statistical robustness. So we usually say that the test, a given test is robust when you can actually violate at some degree the normality and homoscedasticity assumptions, and the test is still robust against the violation of the assumptions. And one of the important things to remember is that the t-test and the Anova are very strong, are very robust tests, both of them against normality and homoscedasticity. So that means that at some degree, they can tolerate some sort of asymmetry, some of lack of kurtosis, lack of normality, lack of homoscedasticity. But you have to be really careful with this because it might be controversial if you, I mean, for example, if the p-value is 0.06, you might actually still use this, the t-test and the, sorry, if the p-value is 0.04, you might actually use this because the tests are robust against normality and homoscedasticity. But again, you have to be really careful with this because you have to consider the non-parametric tests in those cases. But I just wanted to tell you that.
And Wilson, especially when we have sample with more than 100 patients, right? Especially if we have a sample size that is big enough, in general, we can deal with these small violations, right?
Exactly. Yes, that's true. And actually, now that you have mentioned this, let me show you something very quickly. So you don't have to look at this data, at this table. This is only if you are interested in the theory behind the t-test. But Stata does everything for you. You don't need to do this. But if you are interested in this, I just want to explain to you something. This is a t-table. I think I mentioned to you last week or a couple of days before what the t-table looks like. This is a t-table, and then as you can see here, there's again the degrees of freedom that we discussed yesterday, degrees of freedom. But can you see here, when you reach the 120 patients, as Karla said, it tends to go to the infinite, and then the t-value is going to be actually the same for 120 that for 5,000 patients or 10,000 or 20,000 patients. This is important to understand because there is a concept in statistics which is called the central Latin theorem, according to which when you have more than 120 patients, your data tends to have a normal distribution, provided that your data is by nature normally distributed. I mean, there's some exception. I mean, if your data by nature is skewed, so you can have 500 patients and this is still skewed. But when you have more, in general, when you have more than 120 patients, any sample size tends to go to the infinite. So you can see here that the numbers are equal, for example, for 120 patients and significance level of 5% is 1.96, and for 5,000 patients, 1.98 for 120 patients. So I don't know if you got my point.
I'd like to give one example that we had in my group project. We used an outcome, ventilations-free day for COPD patients. And our sample size was 150. And even with this big sample size, more than 100, the ventilation-free days in general is a skewed data. So we was not able to use parametric tests, and we choose non-parametric tests. So I guess this is a real example of a sample larger than 120, but we are not allowed to use parametric tests because the nature of our outcome was skewed. Correct, Wilson?
Yes, that's what I was trying to say. Thank you, Karla. So so the last test, the very last one, because I don't want to overwhelm you, is the Levin test. So I'm going to eliminate this, and I'm going to go for another data. I'm going to clear this. And then again, you have two groups. Oh, sorry. Right. So when we talk about homozedaticity, we talk about equality of variance. But what is the equality of variance? We are just trying to test whether or not the variance for this group is more and less very roughly equal to this one. but obviously they are not going to be equal, but at least they should look like they should have the same dispersion, roughly the same, yeah? So I'm just going to try to find out whether or not this group, the variance of this group, the group 1, is going to be different from this one, in which case, if it's different, I might need to use a non-parametric test, okay? So again, I'm going to rename my variable. So you can see here, right, okay. So I did show you before how to do the Bartlett test. So let's do it again. One way RBT group, and then you can see here the Bartlett test, in which case is 0.57. So that means that there is equality of variance in my groups. And then the other one is the Levin test. And then the Levin test has a very weird name in the Stata, which is ROV-var. So ROV-var is the short for robust variance. And it reminds me of actually the Levin test is very robust. It's very robust against the violation of the normality. Because before running a test for equality of variances, you have to demonstrate that your data is normally distributed. So one of the assumptions for homoscedasticity before running the homoscedasticity test is that the data are normal. If your data are not normal, there's no way to do a homoscedasticity test, and you just need to either transform the data or go for non-parametric test or dichotomize your variable. So ROV-var is the short for robust variance, which means that the Levin test is robust against the violation of normality of your data. So that means that if your data at some degree is not normally distributed, you can still use the Levin test, but you can use the Bartlett test because the Bartlett is not robust against the assumption of normality. Is it clear? So this is one of the difference between the Bartlett test and the Levin test. The Levin test is robust against the normality of the data, and the Bartlett test is not a robust one. So it's very sensitive to the departures of normality.
Wilson, Bartlett's measures the equality of variance, and Levin measures the robustness of the variance.
No, both of them measure the equality of variances. The difference between the Bartlett test and the Levin test is that before running the homoscedasticity, of your data, you have to double check your normality. If your data are not normal, you are not allowed to use Bartlett test, because the Bartlett test is very sensitive to the departures of normality of your data. However, on the other hand, you've got the Levin test, which is a robust test for the assumption of the normality, which means that at some degree you can tolerate some violation of normality, and the Levin test is still stable.
So you have to do both in some.
Not really, because if you are concerned about the normality of your data, if your data are not exactly normal, so you can run a Levin test because it's robust against the non-normality. But if your data is perfectly normal and your p-value is more than 0.05, so you can easily use the Bartlett test.
Okay.
So there is a small difference between the Bartlett test and the Levin test, but obviously they are completely different in terms of the calculations and the equations, because they are totally, I mean, you will see that the p-value shouldn't be the same, but at least they should look similar, okay? So I'm going to test my Levin test. So as I say, it's going to call row bar, and it's very important to understand what the commands mean in order not to memorize the commands. So you really know what row bar means. Row for robust and var for variance, and this is the Levin test. And so again, row bar, dependent variable. So dependent variable is RBT. The comma, don't forget the comma. And by the independent variable, which in this case is the group. So this is the Levin test. It's a little bit funny, but what you need to look at is on this value. This is the p-value, the W50, and this is when the mean equals to the median. So you can use this one. Or when the mean is not equal to the median, you can use this p-value. In any case, so you will see that all the three p-values are more than 0.05, which means that we got homoscedasticity. But I mean, long story short, the p-value that you should look at is this p-value, 0.48, and this is the one you should report in your paper. Something that I forgot to tell you before starting the meeting was that you will very often see very funny outputs. For example, this one, which has not any interpretation in terms of clinical research. And the reason for this is because, as I said, Stata, SPSS, and R, they are not really designed for clinical research. They were originally designed for other disciplines. For example, they use for sociology, they use for economics, and for example, they use for politics. Yeah. So this is not a statistical software package for medicine, for clinical research. Actually, SPSS stands for statistical package for social sciences. So this is SPSS. It was not designed for us. It was not designed for medicine. We borrowed the statistical software from other disciplines like sociology, like economics, like politics, and this is probably the reason why you will see some funny values. For example, this one has no interpretation for me, and I like to say that it might be for other disciplines like sociology, economics, politics. They might have a meaning, but not in our field. So don't be concerned about so many numbers here in Europe. Just go straight to the p-value. Obviously, there are some. I mean, this table has actually interpretation in terms of medicine, but some other numbers have no meaning at all, and this is the reason. Sorry, that was a very short parenthesis. So, so this is the Levin test, and then the very last thing before we finish the meeting.
Wilson, may I have only one quick question? Yes. Regarding equal variance test to evaluate variance, it's related with standard deviation of our sample?
Of course. Just remember that the standard deviation is the root square of the variance. So if the standard deviation is the root square of the variance, so when we talk about variance, we talk about standard deviation as well.
So when we are evaluating this kind of tests, probably the math behind it is to understand if the standard deviation of group 1 and standard deviation of group 2 are equal or different, right?
Exactly.
If
yes, exactly.
the p-value is less than 0.05, we can assume that they are different. So we don't have equal variance, right?
Exactly, exactly.
Thank you.
Yes. As I say, the variance is defined as the root square of the standard deviation. We are just trying to find out how dispersed are our data. And as you know, the dispersion of the data are measured by standard deviation. Number one, you can measure by the variance, which is the background, which is the reason for the analysis of the variance. But whenever you test variance, you are testing actually the standard deviation of the group. So very last exercise. Let me see, where are we here? Let me see. Okay, let me just make up something. T-test dependent variable by independent by the independent variable. T-test. So as I explained to you before, there is the t-value, sorry, the t-test is assuming that you've got equality of variances, but you have means of testing the equality of variance. I already explained to you Bartlett Test, and then I explained to you the Levin Test. I hope that's clear now. And then I would like to ask you a very final question. Do you think when you have, when your data has not homogeneity of variances, do you still use the t-test? Can you still use the t-test with even when your data is not has no homozygosity? Can you tell me yes, no?
No.
No? Say Sophia. Can you test? Can you run a t-test even when your data is not has not equality of variance? What do you think, Daniela?
I agree with them. I think we can't.
We can't. Okay, let's try this. So t-test by group. So I'm going to show you another test, which is the Welsh test. I'm not sure if you've heard about this test, but the Welsh test is actually modification of the t-test. And this is actually a t-test for a sample with unequal variances. So I just wanted to show you the difference. Two sample t-tests with equal variances. You see this? And then two sample t-tests with unequal variances. Okay, So actually, you can test the variance before running the t-test, and even if you don't have equality of variances, you can still run a t-test, as I just demonstrated you. Is it clear for you?
Yes, and the values are pretty similar, right?
Are pretty similar. Why? Because we say that there's homogeneity of variances.
Because in this case, we have equal variance, right, Wilson? So it's expected that we had a similar p-value, because in this case, we don't have unequal variance.
In this case, we don't, but
yeah.
But the utility for this one, let's make up another, just to show you. So I'm going to intentionally change the variance of this one. So as you can see here, hopefully the variance of the group 2 is going to be much larger than the variance of group 1. And you can see here 0.04.
Wow, absolutely on the correct place.
Exactly. So you can see there. So because obviously I intentionally changed this. Yeah. So I'm going to test the row bar. So you can see here, this is interesting. Because I say to you that when the median equals to the mean, you should look at the W50, but when your data is not normally distributed, as in this case, you have to use this one because you have to use the median instead of the mean. So W50 means the mean, and W0 means the median. And because my data is so different, because I made it different, so you should look at this one. You see how interesting is this? So you should look at this one, at this p-value, because my data are not normally distributed, because I made it on purpose. So let's run the t-test. So you can see here, there's still, this is unequal variances and equal variances. It's still pretty much the same, surprisingly, really, 0.18 and 0.17. But anyway, I hope you understand my point, is that whenever you come across with sample with unequal variances, so there is a way to run a t-test even when there is unequal variances.
I guess, Wilson, that this example show us also how robust t-tests are, even violating some assumptions. For continual variables, t-tests are robust tests.
This is a very, very well comment, very nice comment, Karla. I think that might be one of the explanations why. Still, when I made in purpose that the variances, as you can see here, is very, very different, because I mean the minimum was 6, even 4 here, 3 here the minimum, and the maximum for the group 2 was 98, and then for the group 1 the minimum was like 23, and the maximum was like 87 maybe. So there's clearly heterogeneity of the variances, but still the t-test is robust against the violation of, because I clearly violated the homoscedasticity, and you still can see that the p-value is quite similar. So that, I think that might be one of the explanations.
And I guess that's why we use t-test a lot to evaluate continuous variables in medical science.
Yes. So yeah, don't forget that Anova and t-test are very robust against normality and homoscedasticity. But be careful, be cautious, because when you use these, maybe your peer reviewers might question your decision. So you have to really have reasons to use your t-test, and why didn't you use Mann-Whitney or Wilcoxon. So as I promised you, I'm going to finish my my presentation with a slide. So this is the one I wanted to show you, Shova, if she's still there.
That's amazing.
This is, it's a little bit, I mean, don't be overwhelmed, but what I can tell you is that throughout the course, surprisingly, you're going to see all of these tests. So you can see the feature test, the Yates correlation, chi-square test, McNamara, all of these tests you are going to see throughout the course. But I think it's very good to see where, why we are using these tests, and how we, or I mean, it's very difficult, it's very easy to remember when you have a mental structure like this. So you can go straight to the test you have to use. Because if you don't have this structure in your mind, it's very difficult to remember which test are you going to use. So first of all, so you have to wonder yourself, what is your independent variable? So your independent variable, or your explanatory variable, can be continuous, can be a mix of continuous plus categorical, or can be categorical. And then the second question is, what is your dependent variable, or your outcome variable? So your dependent variable could be continuous, could be categorical, again here, continuous, categorical, and continuous, categorical, okay? So the third one, once you come up with this, with the answers for your questions, so is it non-parametric distribution, non-parametric test, or parametric test? It depends. Is your sample having a non-normal distribution or a normal distribution? And then, is it non-dichotomic or dichotomic? Non-dichotomic or dichotomic? And for this one, you have to wonder yourself, is it pair or unpair? Pair or unpair? So the basic ones, I believe, are going to be these ones. This is the ones you are going to see first. And so we say that if the dependent variable is continuous, for example, as we say, we use the example of the RBT. this is a continuous variable. And then your independent variable is categorical. Why categorical? Because you've got groups, and the groups are categorical, group 1 and group 2. So because of this, you have to use this, this test. So is your data pair or is your data unpaired? Yeah. And then the other question is, your data non-dichotomic or is your data dichotomic? And again, the same question for the unpaired. And then the very last question, is it parametric or non-parametric? And based on these 4 or 5 questions, you are going to come up with the right test. So if it's parametric, unpaired, dichotomic, your dependent variables is continuous, and your independent variable is categorical. So this is the t-test. Yeah. So the analogy for the t-test is the Mann-Whitney test when you can't run the t-test because of problems with the normality. And then when your data has got more than 2 groups, we already discussed that Anova can be used for 2 groups. But if we got more than 2 groups, so you can use Anova. But if your data are not normally distributed, so the right test to use is the Kruskal-Wallis. And then if your data is paired, so obviously you have to use the pair t-test, which we discussed. We didn't have any time to discuss the Wilcoxon. And then if your data are paired, and this was the Mann equations, so you can use the Anova because your data is paired. So you really need to use the repeat measures Anova. And finally, if there's no normality of your data, is no homoscedasticity of your data, so you have to use the Freeman test. Same for the other ones. I'm not going to go through this because you're going to see all these tests in a few months' time. And the other one is the comparison between a categorical dependent variable and a categorical independent variable. So in that case, you have to use, if it's a pair test, you have to use Cook-Cochrane or McNemar, or if it's unpaired, you have to use chi-square, Yates, Fisher, or sorry, something happened here. Or the Manton and Hensel test. I think that finishes my intervention. Sorry, I didn't have time to discuss with you this, but this is going to be like another hour to discuss these tests and these tests. But I hope you have enjoyed my presentation. Thank you very much for joining us. I'm very happy to take any questions if you like. And I hope you have learned something new with my presentation.
Thank you, Wilson. This is like 3 years of statistics.
Wilson, I'd like to first congratulate you. It was an amazing lecture. Thank you so much. I'm sure we all learned a lot. And this record lecture, I'm sure that will help a lot. So thank you so much for your time, and thank you all the students for the participation. Thank you.
Thank you everyone for coming in. Thank you for joining us. Please feel free to ask any questions. Feel free to contact me. You got my email. I don't usually see my River messages on a regular basis. So if you have any questions, just drop me an email, and I'm happy to help as much as I can, or you can contact any of your TAs as well.